Hello and welcome to your first neural networks lecture. So today I just want to cover some of the basics, like an overview of what neural networks are, because neural networks are really flexible and some can get really complicated, and it's a lot more material than I want to cover here. You could take an entire class on this, and you could actually literally take an entire class on this next semester. So I'm just going to cover some of the basics here, like the basic ideas of what a neural network is. So neural networks are just algorithms. They're just a way of taking input data, doing some calculations, and outputting something that you want, whether it's a continuous value or a category or a probability. A neural network just is a way of calculating what you want, your output, from your inputs. And you often see this type of structure, and it might make you think of a brain with all of its connected neurons, which is why a neural network is called a neural network, because there are some aspects of it that mimic the human brain. Now, neural networks, like I mentioned before, are really flexible and they can get really complicated, but that doesn't mean that they have to be complicated. In fact, today I'm going to talk to you about a couple models that you should be familiar with if you've been paying attention in class, and talk about how we would represent them as a neural network. So the first one I want to talk about is linear regression. And hopefully we're familiar with linear regression because in linear regression, you just take a series of inputs and we do some calculations and turn it into an output, usually a continuous value. So let's talk about the different parts of a neural network in the context of this linear regression. So in linear regression, right, we have our inputs. That's one of the main things that we have, is what is the data that we're putting in. And in this case, in a neural network, we usually represent inputs, so each individual variable, as a node. These little circles here are nodes. And the reason that we call them nodes is because we're essentially just storing a value in them. A node is a way of storing a numeric value. So when we have an input node, those input nodes contain whatever variable it is that we're plugging into our linear regression. In this case, it's age, sex, salary, and rent, and the output that we're trying to predict over here, label that, is the amount that someone spends on video games. So when I said that a neural network is just, you have some inputs, you have some outputs, and then you have some calculations in the middle that take you from that input to that output, well, that's what this is representing here. You can see the lines that are highlighted in green. We call them in neural networks, we often call these weights, but you can think of them in linear regression as the coefficients from our linear regression model. And this just shows how all of the nodes are connected. So you can see that to get the output node over here, we take all of the input nodes, weight them by whatever their coefficient is. We add something called a bias. Now, this is just like the intercept of your model, so you can just think of it as an intercept, but technically in neural networks, we call it bias. So you're taking your weighted coefficients, you're adding an intercept, and when you add all of those together, you get your output node, or your guess for how much money someone spends on video games. Now, the last thing that I want to talk about the structure is that this thing over here, the activation function. So an activation function is just, do we do some algebra to the output value before we return it to you? And in this case of linear regression, we don't. All we do is we take the individual input values, we weight them, we add them together, we add a bias, and then we output that as our guess for how much someone spends on video games. In the next slide, we'll talk about a different activation function, but for now, you can just realize that this doesn't really have one, or it has something that we call a linear activation, where we're just returning the value as is. Now, that's the structure of the neural network. And the other thing that we have to think about is, how are we training this network? How are we getting the network to learn what is the best answer? How does it make the best predictions? Well, that's actually also very similar to what we talked about in linear regression. We have some kind of loss function. Sometimes people will call this a cost function as well. And in terms of linear regression, we usually use the sum of squared errors or the mean squared error, which is just the sum of squared errors divided by the number of data points. And what we're doing is this loss function is something, as we talked about before, that we want to minimize. We want the loss to be as small as possible. And that is exactly how your neural network learns. It iterates through all of the data and tries to minimize that loss function. When it's effectively minimized the loss function, then it's done training and it'll output your model for you. So let's talk about it now in terms of logistic regression. And this should look really similar. In fact, the only thing that's different is in this output node here. Two things. One, now because it's logistic regression, we're actually predicting a binary variable. We're predicting whether or not someone is a Twitch streamer. And you'll notice this little S, we sometimes call this a sigmoid activation. And remember when we did logistic regression, we said that instead of predicting a probability or predicting the odds, we're actually predicting the log odds. So we have log of p over 1 minus p. And this activation function is essentially saying, I'm going to predict the log odds and I want you to return to me a probability. And so this sigmoid activation function just represents the fact that before we return the values to the user, we are going to put it through a little bit of algebra so that we can turn our log odds into a probability or even a binary 0, 1. Now, the other parts of the model are exactly the same, and we talked about this in our logistic regression lecture, that logistic regression is just linear regression in disguise. And I think that becomes even more clear when you talk about logistic and linear regression in terms of how they would be structured as a neural network, because you can totally see, look, the only difference in the structure is right here. We put it through an activation function before we return it to the user. Now, just as we talked about in the logistic regression lecture, the loss, we're using this formula right here, which, as we talked about before, is essentially a measure of how far was your guess from the truth, which is either it was or it wasn't part of that category. Okay, so hopefully this gives you a good overview of what the structure and a little bit about what a loss function is in terms of a neural network. But neural networks aren't just for doing the simple models that we've talked about in class, like linear and logistic regression. You can build much more complicated models. And there's three main things that you want to think about when building what's called a feed-forward neural network, which is just one of the simplest types of neural networks that you can have. The first thing that you want to think about is the structure. In the linear and logistic regression examples, we had a very simple structure. We had one layer of inputs and one layer of outputs, and then we had a bunch of weights connecting them. But you can have multiple layers in a neural network. You don't have to go straight from input to output. You can go from input to another layer, 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 all the way out to the output. However many layers that you want, although obviously you have to think about your computer having to fit all of these parameters, but you can technically have as many layers as you want. And just FYI, when you hear about deep learning, it usually means a neural network that has 2 or more layers. The second thing that you have to think about is the connections between your layers. So you can see here that we have something called dense connection. Every node in one layer is connected to the node in the next layer, and so on and so forth. But that doesn't have to be the case. You can have some nodes connected to other nodes and not to other ones. The last thing that you want to think about for each layer is the activations. We talked about activations in the logistic regression example because before we return any value to the user, we wanted to make sure that we put it through some algebra so that we were giving someone a probability instead of the original log odds that a logistic regression model spits out. But you can have activations at any point in any node in your neural network, and you have to think about what are the activations that you need or want in each case. Now, I'm sure there's going to be a lot of questions about how do I pick these? What do I do? And in some cases, there aren't really good answers. Sometimes building a neural network can feel more like art than science. There's not a lot of hard, fast rules that you have to follow, although some people do have a lot of good rules of thumb for how you should build a neural network. And I'm not going to cover a lot of those here because there are other classes that you can take in this series that will cover neural networks and all of the details. But for now, just know there's a lot of flexibility. You can pretty much build any type of structure with any type of connection and any type of activations that you want. Okay, so I'm going to save this for the next lecture, and I will see you for your Python lecture.